Inside a four-story printing plant in Brooklyn in 1902, the humidity has thickened the air to the consistency of warm soup. For the ink-smeared workers inside, the July heat is a physical weight. The mechanical crisis centers on the paper. Because paper is hygroscopic, it acts like a sponge, drinking water straight out of the humid air. Throughout the production day, the massive sheets running through the presses are physically swelling and shrinking as the moisture levels fluctuate. Multicolor printing requires running a sheet through the press 4 separate times. If the paper changes dimension by even a fraction of a millimeter, the cyan, magenta, yellow, and black ink layers slide slightly off from one another, turning expensive magazine pages into blurred, wavy trash. To solve this specific mechanical glitch, the company turned to a 25-year-old junior engineer and former farm boy named Willis Carrier. Carrier was tasked with fixing a localized printing error, but the sketches he produced would eventually trigger a chain reaction that reconfigured human civilization. Escaping the summer heat is a 4,500-year-old human obsession. The Romans plumbed cool aqueduct water through clay pipes embedded in the walls of wealthy homes, creating a primitive form of radiant cooling. In the desert, Persians engineered tall wind catchers. These towers captured high-altitude winds and forced them down through underground canals to naturally refrigerate the rooms above. By the 1850s, an American physician named John Gorey was using the thermodynamics of gas compression to mechanically produce ice in Florida, hoping to cool the wards of his malaria patients. Every civilization prior to 1902 shared the same fundamental limitation. They could lower the temperature of a space, but they could not mathematically guarantee a specific, consistent outcome. Carrier succeeded where these empires failed by applying a childhood habit. As a boy, he struggled with fractions until his mother taught him to visualize math by slicing apples into halves, quarters, and eighths. Carrier approached the impossible problem of weather by breaking it down into those same simple, solvable units. Carrier's initial fix for the printing plant involved routing air over coils chilled by cold well water. As the warm, moist air hit the cold metal, the water vapor condensed out and dripped away, leaving the air both cooler and drier. The paper held its shape, but the pressmen discovered a side effect. With the humidity removed, they could suddenly think clearly and work efficiently all day long, regardless of the July heat. While Carrier had solved the immediate glitch, he hadn't yet distilled the science behind it. That insight arrived months later on a foggy Pittsburgh train platform as he watched the gray mist swirl around the gas lamps. Carrier realized that by drawing air through a fine spray of water to create an artificial fog, he could force that air to a specific saturation point. By controlling the temperature of that spray, he could dictate exactly how much moisture the air would hold when it exited the machine. In 1911, he formalized these relationships into the rational psychrometric formulae. This map of how temperature and moisture interact allowed engineers to calculate exactly how much cooling a specific building needed. Carrier hadn't just built a better fan, he had authored the Magna Carta of indoor climate, transforming cooling from an architectural parlor trick into a reproducible mathematical certainty. By 1922, Carrier had developed the centrifugal chiller. This machine was smaller and safer than previous industrial models, making it feasible to cool massive public spaces for the first time. This technology arrived just as the movie industry was struggling with a seasonal financial graveyard. In the 1920s, theaters were dark, suffocating boxes that lost nearly all their business during the summer months. The turning point was Memorial Day weekend, 1925, at the Rivoli Theater in Times Square. As Carrier's new ceiling registers began delivering cool air, patrons stopped using their hand fans. Watching from the audience, Paramount Pictures head Adolph Zukor noted that the public was going to like it. The summer blockbuster was born as a direct result of HVAC engineering. Hollywood realized they could command mass human behavior simply by offering artificial winter during the hottest months of the year. Following World War II, the invention of the compact window unit moved air conditioning from a commercial luxury to a domestic expectation. By 1953, Americans were buying over 1 million units a year. This mass residential cooling physically redrew the demographic map of the United States. It allowed for the explosion of Sunbelt megacities in regions previously considered too hot for dense habitation. Between 1950 and 2000, the population of Texas grew by 170%. Today, entire sectors of the economy are reliant on Carrier's math. Modern hospital surgeries, semiconductor manufacturing, and the data centers that power the internet all sit atop a layer of climate-controlled infrastructure. Without the ability to precisely control indoor weather, the economic rise of the American South would have been impossible, and the hardware of the digital economy would literally melt down every July. There is a dark thread in this legacy. The early chemical refrigerants required for mass cooling, known as CFCs, turned out to be responsible for chewing a massive hole in the Earth's ozone layer. While those chemicals were phased out, their replacements are potent greenhouse gases. As developing nations adopt air conditioning and global temperatures rise, the massive electrical demand of these units creates a feedback loop, accelerating the very warming they were designed to mitigate. To address this paradox, engineers are now merging Carrier's precision with ancient passive cooling methods, revisiting Persian-style wind catchers and desert-inspired ventilation to reduce the energy load. We live inside Willis Carrier's 1902 idea every summer, but the machine he built to make heat tolerable is now one of the primary technologies making the planet hotter.